Two approaches to urban metabolism studies involve the quantification and assessment of energy and material flows, and they are known as Emergy and material flow analysis. Emergy and material flow analysis are two schools of thought when it comes to methodologies to measure and quantify energy and material flows in urban areas. The two methods are related, non-conflicting schools of urban metabolism that capture the information on urban metabolism diagrams using different units, which also implies a different conceptual way of looking at energy and material flows. The first is Emergy, a word coined by Howard Odum, which has scientific roots in thermodynamics and systems ecology, and historically it joined the two words referring to embodied energy. Metabolism is described in terms of energy equivalence, relating all energies and all flows back to the main source of energy, which is the sun's solar energy. Howard Odum was an American systems ecologist who lived between 1924 and 2002. He earned his PhD from Yale, which was also where he started his lifelong collaboration with his brother Eugene Odum, and together they co-authored the first English-language textbook on systems ecology called Fundamentals of Ecology in the 1950s. He specialized in ecosystem ecology and thermodynamics, which were informed by his work on general systems theory. His analysis of energy flows in ecosystems focused on representing urban processes in terms of solar energy equivalence as a result of recognizing that when two or more different energy sources drive a system, they cannot be added without first converting them to a common measure that accounts for their differences in energy quality, hence embodied energy. Previous research did not account for qualitative differences of mass or energy flows, and so he coined the term Emergy to track and account for the metabolic flows by measuring the solar energy used directly or indirectly. The other method is material flow analysis, which more broadly expresses a city's flow of resources in terms of mass fluxes. It measures the materials flowing into a system, the stocks and flows within it, and the resulting outputs from the system to other systems in the form of pollution, waste, or exports. This method typically includes a system boundary, and the processes occurring in the system are visualized in addition to the flows which enter, accumulate, and exit the system as a result of all the processes within the system. Material flow analysis, as it applies to urban systems, was developed by Bacchini and Brunner in the 1990s and others before them to provide a framework for analyzing the manner in which urban areas transform natural resources, and it is a method that is frequently used in engineering, with the emphasis being placed on the flow of specific materials. Bacchini and Brunner are the authors of Metabolism of the Anthroposphere. Peter Bacchini is a natural scientist from Switzerland and was a professor of material management and disposal engineering at the Department of Civil, Environmental, and Geomatic Engineering at the Swiss Federal Institute of Technology, ETH Zurich. And Paul Brunner is specialized in material flow analysis and urban metabolism, and was a professor at the Institute for Water Quality, Resource, and Waste Management at the Vienna University of Technology in Austria, TU Wien. In a side-by-side comparison, the Emergy method emphasizes the use of a standard unit of measurement to calculate energy, nutrient, and waste movement in the biophysical system. The unit chosen was solar Emergy joules. However, the ability to convert all urban processes into solar Emergy joules has proven to be difficult to understand. Now, the other method, material flow analysis, quantifies energy and material flows like raw materials, nutrients, and food in standard mass units. Data is represented in mass, for example in tons, to measure the weights of material inflows and outflows. Based on the principle of mass conversion, where mass in equals mass out plus stock changes, material flow analysis measures the materials flowing into a system, the stocks and flows within it, and the resulting outputs from one system into other systems. In an urban design context, it shows relevant processes and flows of resources for a component of the urban metabolism and quantifies the stocks and flows of resources, including recycling, as well as quantifying the absolute flows across a system's boundary. This method provides decision makers with quantitative evidence to evaluate self-sufficiency and resource efficiency, and has been widely used, so we'll focus more on this method. Bacchini and Brunner identify the 4 key resources that, at a minimum, should be included in a material flow analysis of an urban area, and they include water, food and biomass, construction materials, and energy in all forms. They also outlined the general methodology of urban metabolism using material flow analysis in 5 steps as follows. First, it begins with a definition of the scope and purpose of the study, that is, the objective of the study being done and/or the research question that the study hopes to address. Then a system definition. This involves setting the boundaries of space and time. So in carrying out the analysis, one would determine what the system is, that's the space, and for which year or range of time. And a definition of the relevant processes, goods, and substances need to be established, including identifying how they are linked. Oftentimes, indicator materials such as carbon, nitrogen, and phosphorus are chosen based on the nature of the system. Next is data collection or acquisition. This is the way in which the processes and flows are quantified. And this can be done in many ways, including measurements, market research, expert judgment, best estimates, interviews, and hands-on knowledge. Then comes material balances, modeling, and scenario building. This is the step where results can be integrated into static or dynamic mathematical models to assess the impacts of various decisions on specific material stocks and flows. And lastly is the interpretation of results. Once numbers are attached to the flows, in and out, and the quantities loaded into the model, a comparison of results against environmental standards, sustainability indicators, or other assessment approaches can be made, and perhaps one can make an evaluation or inform policy or introduce innovations to manage the flows based on the results. I'll walk you through what these steps look like in reality as an urban metabolism diagram is developed using material flow analysis and using examples from cities in literature or practice. So, first step. Step 1. Definition of the scope and purpose of the study. This is important to know at the beginning to set the objective of the study and the question to be answered, which is the reason why one would carry out a material flow analysis. An example of a question could be, how has the urban metabolism of a city changed in 30 years? The reality could be that perhaps we want to see the changes in freshwater inputs and wastewater releases, say in Hong Kong, and the time frame between 1971 and 1997. This was actually posed in a study of several cities and several resource flows in an article on the changing metabolism of cities by Kennedy et al. In 2007. Step 2 is system definition. The system's physical and temporal space needs to be defined so that it's clear what is being included and what is not. If our system is a country, the physical boundaries are clear because countries have clear geographic borders. Otherwise, it's not quite obvious. For urban areas and systems, we would be defining it by identifying that boundary of interest to show what's in and what's out. An example of a system definition is shown here from Saheli and Kennedy's research on a system flow model for the urban water system in the city of Toronto. In terms of time, the data collection was for the years between 2001 and 2010. The diagram here shows the urban water system starting with the water source on top and flowing to the water withdrawal and treatment, water distribution, and end use, which then takes wastewater to sanitary sewers and wastewater treatment, which results in treated effluent back into the system. Other inputs are involved in the process. So as shown on the left of the diagram, we have natural gas, energy, and chemical use as inputs into water withdrawal and treatment, energy and chemical usage in water distribution, sometimes hot water heating for end uses of water, energy use for sanitary sewers, and natural gas, energy, and chemical usage in wastewater treatment. To the right of the water flow process, there are water losses as a result of water distribution. Water end uses result in water that makes its way into combined sewers though inflow and infiltration could also seep into the sanitary sewers and into combined sewers. And wastewater treatment results in solids that are treated and sent to disposal, or could be included in an energy recovery process. On the far right is a water system intercepting rainfall that flows into a stormwater collection process, either into combined sewers or storm sewers. In the case of combined sewers, the city may experience combined sewer overflows. What's important to note here is that the urban water system is mapped out, showing the inflows and outflows and interactions with other relevant systems, and also shows what the study will include and exclude. In this study here, the researchers chose to include all processes shown in white boxes and all flows shown as solid lines, and excluded all those processes shaded in gray and all flows shown as dotted lines. The boundaries of the system is now clear, and what is included is relevant to addressing the scope and objective of the study. Here's another example to visualize system definitions by identifying system boundaries, and these images are borrowed from Oswald and Bacchini's NetStat. This is a system boundary around one particular phase of the building cycle, and that is the building operation process, showing inputs as energy source, water, and building materials, and outputs as exhaust fumes, wastewater, and solid waste. Also from Oswald and Bacchini, we could zoom in into the building operation system to look more closely at only the water flows, but for all the detailed processes within building operations, like water uses for washrooms, hygiene, cleaning, washing clothes, kitchen, and plants. All together include inputs from the water distributor, which comes from a fresh water source, and flows out to a wastewater collector system and produces wastewater that will still need to be treated. This system border, shown again as the dotted red line, shows the differentiation of the building operation system into sub-processes for the resource of water. Or rather, we can zoom out to other processes in the building cycle, also from the NetStat by Oswald and Bacchini, that shows the integration of the building operation process into a regional resource management system, with flows and stocks of materials and energy. The system border shown here as the dotted red line includes building production, building operation, and building demolition. Together, they interact with the infrastructure system that includes infrastructure production, infrastructure operation, and infrastructure demolition. Both systems require building material production that is sourced from organic and inorganic resources. Or we can zoom even further out to show a very large system border that includes building operations that we saw earlier in the regional resource system, fitting into what is referred to here as households on this diagram from Oswald and Bacchini, and is included into the overall system that also has agriculture and industrial processes as part of this large system. This particular system shows the flows of nitrogen and phosphorus in units of kilograms per capita per year. Step 3 is data collection. This could be as detailed or as aggregate as needs to be or as is reasonably available. Of course, the better the data going into the analysis, the better the results coming out of the model. The biggest challenge is always trying to find reliable data. Here's an example of a data collection exercise for an urban metabolism study carried out for 4 neighborhoods in the Greater Toronto Area by Kodoban and Kennedy. The neighborhoods are Trinity Bellwoods, Crescent Town, Don Valley Village, and Milliken. The researchers made every effort to use data from the same source for the year 2000, but inevitably, depending on the availability of data, some inputs included data between 1990 and 2001. Data collected included location, predominant building types, and years of building construction. Inflows included net all-wave radiation, energy, which includes electricity, natural gas, heating oil to buildings, fuel to public transit, and fuel to private transport, water, food, and total energy. Outflows included latent and sensible heat, anthropogenic energy, wastewater, and solid food waste. To show the range of sources for data acquisition, neighborhood data was obtained from the Neptus Foundation and the City of Toronto. Food calculations were performed with data from Statistics Canada. SI Metric and United States Department of Agriculture. Food waste, water, and wastewater data are taken from the City of Toronto reports. Ontario residential waste data from the Ministry of Environment were used to calculate Toronto residential food waste. The building energy data were obtained from a national database and from a study by a local consulting firm. Transportation data were from Transportation Tomorrow surveys carried out by researchers at the University of Toronto. Where Canadian data was not available, data for other countries were referred to, such as data on cooking water consumption and wastewater generation, which were adapted from Bacchini and Brunner's Metabolism of the Anthroposphere, among others, and calculations of food energy consumption by the human body were performed with data published in the academic literature, and Toronto's retail food waste was estimated from New York data for its similarity in consumption. Step 4 brings us to material balances, modeling, and scenario building. This is the step where the data collected earlier is loaded and processed for analysis. In its simplest form, quantities of inflows and outflows come together in a balance of materials formula that applies the mass conservation principle, according to which the mass of inputs in a process equals the mass of outputs plus a storage term. In this equation here, M is mass, and P and Q represent summation over input and output terms. In other words, inputs equal outputs, but if the numbers are not the same, the difference of quantities exists as amounts stored in the system. A more detailed set of calculations have been compiled by Kennedy in a book chapter on a mathematical description of urban metabolism, where he presents 25 closed-form equations that represent essential interrelationships between the major components of metabolism, which include materials, water, nutrients, energy, and contaminants. Short of displaying all 25 equations here, Kennedy presents the model used for urban metabolism by material flow analysis as the diagram shown here, that shows the system's boundary as the dashed outer line, within which is an urban system that includes peri-urban areas, aquifers below the city, and the urban atmospheric boundary layer above. The model shows flows I, arrows pointing inward, outflows O, arrows pointing outward, and storage S of the main components of the urban metabolism. Also included are annual internal fluxes, Q, for example between surface and subsurface parts of the urban system, and the internal production, P, of food by urban agriculture. The subscripts are M for materials, W for water, E for energy, and F for food. And finally, step 5 is the interpretation of results. The results are the urban metabolism diagram produced using the material flow analysis. What we make of the urban metabolism diagram is subject to our interpretation and responds to the objective and purpose of the study that was set earlier on and for which it was started. An example of the results is an urban metabolism diagram reproduced from Kennedy et al. Showing the Toronto Portlands in a sustainable scenario in the year 2050. A few interpretations resulting from this diagram are that many flows that produce waste outputs are being fed back into the system as inputs into other processes, and therefore creating circular flows and demonstrating a more sustainable use of resources because of reuse. Another is ash resulting from the IGCC, Integrated Gasification Combined Cycle, to produce energy is used into concrete production to make building materials. And sludge from wastewater treatment plants is used to make the soil in community gardens. And one more, MSW on the diagram is municipal solid waste from the city, where the methane is captured and used as energy to power the IGCC. To end with an effective quote by Kennedy and Hornweg, who are experts in their respective fields of urban metabolism and sustainable cities, they say, if cities are to take sustainability seriously, then collection of urban metabolism data has to become a mainstream activity for all large cities.